You're welcome. You're welcome to September FANOG monthly meeting. Usually we have a monthly meeting every month, and we bring in resource person across the globe to speak to us. And this month, we are glad to have Dr. Lateef Olakunle Jolaoso. Dr. Jolaoso is a well-known researcher. He has published over 120 papers that are in Scopus, and he has over 1,300 citations also in Scopus. So he's a well-known author, and he's also editor to some top rated journal. And today, Dr. Lateef will be talking to us on optimization problem in real world. And of course, his affiliation is a faculty member of School of Mathematical Science, University of Southampton, UK. So it's a pleasure having him to talk to us. So Dr. Jolaoso, you now have the floor. I want to welcome everyone. Thank you. So Dr. Jolaoso, you have the floor now. Many people are joining
Muted.
us. I'm
Yeah.
going to admit, yeah.
Can you hear me now? I think I
Yeah.
was muted. Yeah.
Okay.
Yeah, thank you very much, Prof. I really appreciate inviting me to your monthly meeting. I think one thing I like about this is the fact that we're trying to come together as researchers, most especially from the developing countries, because this is one of the things we are lacking from from developing countries, among which is Nigeria. So having a forum like this where you have people, you bring people to talk about the current trend and research is very, very okay. And I believe this as well would be very helpful to our young colleagues who are just coming up, most especially the postgraduate students, having an opportunity to meet with people who are working in their field of area of research. So I appreciate your efforts on this. Good morning, colleagues. Today we'll be looking to optimization problem in real world. Can I just take a few minutes to share my screen? I think I'm not able to share my screen. I think you have to give me permission to do that.
Let me reset to allow you to share your screen.
Okay, yeah, while we are waiting that, the essence of today's talk would be to showcase some of the importance of optimization
I
problem
think you can try
around
to
the
share your
world.
screen now.
All right. Okay. All right. Yeah.
Yes, thank you. We can see your slide. Uh,
Okay. So like I said, one of the main reasons for today's talk would be on optimization problem in real world. What are the applications of optimization problem? There are several of them. Yeah, we know some about them. And most importantly, looking at the fact that there is a bridge between mathematics and that artificial intelligence, which happen to be the current trend in terms of application of technology in the real world now. So it's kind of interesting when we look into how mathematics come into play in artificial intelligence. And one of these is through optimization because most of these models in artificial intelligence, for example, machine learning, are all perhaps optimization problem, so which could be solved using some tools in mathematics. And also to buttress about that is the fact that we have fixed point theory, which happened to be my initial background because I was formerly working on fixed point theory before I diverted into optimization problem. So the beauty of fixed points has was showcased in terms of solving some of this problem. And that's why I kind of bring about this topic, try to see how I could make this as a motivation for most especially the postgraduate students and other colleagues who are working on this area of research. So I'll be a little bit kind of slow in terms of the presentation. I want it to be something of an interactive section, so I could probably try to ask questions to see that people are following what I'm saying. So yeah, before we go the theoretical aspect, we will have to talk about the definition. Email. Yeah, I know almost every day, every one of us got spam mail from whosoever around the world trying to see if they could get something from us. However, when this email comes into the spam box, do we know how it goes into the spam box? At least out of 100%, a larger percentage of them going to the spam box, not the main box. How is our email able to identify which one is spam and which one is not spam? So this is a problem that we ought to have thought about, especially for those who are doing mathematics. Yeah, people in machine learning will know this, of course, because this is a machine learning problem. But however, the mathematics behind it, we know about it. So that's one of the beauty of mathematics, because all what is happening there is just a classification problem using linear regression or whatsoever, logistic regression, whatever we are using, which main source is just mathematics. So the ability to identify which mail is coming. Sorry?
How about that?
Okay, I think it's just nice. So yeah, so the ability to identify which mail is spam and which one is not spam is one of the beauty of mathematics to the world. And then also we have a very beautiful image here where you have image processing or image identification. Just recently, Apple announced they are releasing a new version of their phone of the handset, and they call, I think, Apple 16, they call it iPhone 16. When you look at the key thing they are doing is just trying to improve on the image quality of the phone. What you have in iPhone 15 is different from what is presented in iPhone 16. And it goes on and on and on like that. Like, just a simple example of this is we cannot compare the quality of image we had several years ago with the quality of image we have today. There has been some improvement, regularly improvement on this area of aspect, like trying to improve on the quality of the image. This is just application of mathematics as well, via image processing, trying to clear the noise from the original image. How best can it clear the noise? And doing this, they are solving a model which purely is mathematics. So this is also another important, a beautiful application of mathematics in the real world. However, the mathematics behind it, maybe we will try to struggle with the theoretical aspect, why we leave the engineers to do the application aspect. But nevertheless, it should be at our mind that or if there's something we could do as well to see how our theory, how our results are being utilized in terms of the real world application. That's where our work would be appreciated. And then finally, I have the third image here where I have the traffic. Then yeah, we have to sort this. It's not in line. We have our traffic on highway. How is this being solved? Yeah, this can be solved probably via some assignment programming and other stuffs like that. But what we have to know about that as well is that this is just a purely mathematics problem as well, because trying to solve this traffic problem in such a way that there is an efficiency in the utilization of the road. We have people, the number of people on the highway at a particular time is being optimized in such a way that people time are being utilized properly. So this can be modeled as mathematics, a problem of optimization problem, and solved via our mathematical tools. So which is the third application of mathematics, most especially optimization, I mean. another top application optimization in the real world. So these three examples I brought about are things that my research fall into. So I have the first one was the image, the three aspects I've tried to focus my research on in recent days. So most of the work I'm doing in the more focused on application in these three key areas of research. My thought is an optimization problem. Yeah, maybe in our everyday life, we can either directly or indirectly from trying to maximize our utility and our time, make good use of our time, the time allocation we give into resources, are also application of mathematics. But coming to that in terms of in the mathematical concept, when I say what is an optimization problem, some things have to come into fact. I have to define that, and the key is the objective function. There is a function that beautifully or ugly, and I have to minimize or maximize the function. Perhaps in such a way that this variable x is coming, call this x a feasible set. That is a set of solution of the problem. Also, we have some set of constraints which can either be an inequality or an equality problem, not depending on the problem I'm dealing with. So it can either be of the two or perhaps both of them. Is the function health subject to some constraints? Yeah, this is a vector because it's going to be in several lengths, and likewise as well the equality. I don't know if you are following. Can you identify or just
Yes,
say
we are
if you are
following.
following so I can make it in?
Yes, we are following loud and clear.
Okay.
Yeah, go ahead.
Now, going to before we start talking about the method of solution for solving optimization problem, the key things have a very major role to play in the problem we are solving. The nature of the function. Is it convex? Is it non-convex? It can either be smooth as well, non-smooth, perhaps. So all these are the properties of the function that will determine what types of method we have to use to solve the problem. As we move along, we'll see how changes from one form to another form. And all these leads for that problem. I will talk monotone and as well as variational inequality. Now I have this here. Here, pose a question here. I have two curve, one on the left, another one on the right. Can I know which of these two is convex? If I define what is convexity in terms of just having a graphical illustration of what convex function is. Though I don't know, do we have graduates here as well? Prof, are you students?
Yes, yes, we are with you.
Yeah, I'm just asking if any of them can identify which of these two is convex.
Okay.
The first one is convex.
Is it the one on the left or the one on the right? Oh, sorry, I put it comes. The answer is there already. Sorry. Yeah. So the reason I asked the question is that I'm not too sure that they are with me because most especially, yeah, the presentation is for the larger audience, but I kind of make it more communicative with the postgraduate student. The one on the left here is the convex, and the reason why it's convex, I don't know, I could have asked, why do you say it's convex? Any of the postgraduate students tell me why
Yeah,
this
a
on the left
postgraduate
is
student should
convex?
answer that. Why do you say this? The first is convex and the second is not? I think that's the question. Anybody? You can unmute yourself if you want to talk. Then after talking, then you can mute yourself back. Anybody among the audience?
Yes.
Why is the
Yeah,
first
please,
convex?
can you try to answer if why do you say the one on the left is convex?
Please check your, some
Hello.
people are, uh,
Is anyone answering?
Yes. Yes.
anybody?
Let me attempt.
Okay.
So, because if you draw a line from on the left is convex, because when you draw a straight line from one end to the other, you can have everything inside it. But the one on the left, on the right rather.
Yeah. Okay, I think he's making a point here, which is very, very sensible. Thank you for that point. I really appreciate. Yeah. In a layman term, we can say the one on the left is convex because we can always move around points around its neighborhood where we have when we draw a straight line, I mean, it will always be within the curve. It won't go outside of the curve. If I draw a straight line from this point to this point, it's going to be entirely on this curve. But I can't do that here. If I have to draw a point from here to here, or from this point to this point, I will go outside of the curve. From here to here, I will go outside of the curve. And also another reason is you can say this is because of the curvature, the way it looks. So as well can also determine which is convex. If it fixed up here, you can see here we have the convexity facing up, and here the other way around. So it's not always entirely like that. So you have the two is where we have this is convex and this is not convex. The reason why I ask this question is because convexity has a very major role to play in optimization. Like I said, the types of the function f determine how you solve the problem. So one of the key things we have to be very attentive about is the function we are dealing with, is it convex or it's not convex. So after that, another key important property of the function we deal with in optimization is smoothness. Yeah, I think we have some time. We can just have like the reason I'm trying to bring this up is I want to say yeah, I will basically trying to shine the postgraduate student to see probably they have not just the theoretical concept of what they are learning, but most importantly, the real life or the illustration of what they are learning as well as coming into play. So if I ask you in a simple layman term, like you want to explain, assume I'm your baby brother in nursery school, and I had the word smoothness for the first time in mathematics. How will you explain that to me? To the postgraduate student, please, if any of you can just answer that. How do you explain the term smoothness to a small child?
Yeah, if you can unmute yourself, a PG student can unmute himself and answer that. Smoothness, explanation, layman.
Good morning, everyone.
Yeah, good morning.
Okay, if we are talking about, I want to explain to somebody about the smoothness of a curve. I should be able to tell the person that curve I can move without I can move without having an edge. Maybe if you have a curve that there is no vertex, that you can move smooth, you can move without any obstruction. Because the first one is smooth, while the second one is not smooth. Because if you move, when you get to the vertex, you have to wait and change your direction. But this one, you can move without, you can move on the line. You can move completely on the line without any obstruction at the edge. The second one is not smooth because at the edge, there's a point of a discontinuity there because it is not at that point. It will be a bit rough. I don't know if I should use the word the second one is like a discrete. The second one is like a discrete curve.
Yeah, thank you very much. That's very lovely. Yeah, it just gave a simple explanation of smoothness. Or in other words, just to make it more technical a little bit, I call it differentiability. Is this function differentiable entirely on its space? Which is, it is, yeah, actually. Like I said, you can always move around without any obstruction in terms of how you change the direction. But in this case, yeah, it's not like that. At this point, there is a point to at this point. This function here is non-smooth. In other words, it's not differentiable. Not entirely not different. It can be differentiable in terms of the subgradient, but in a simple normal gradient or normal differentiability, we say this is not differentiable. So yeah, thank you for that. I really appreciate your efforts to answer the question. So these two things are very important when solving optimization problem. You want to know if your function is convex and if your function is smooth, because when the idea of the method for the solution will be determined based on these properties we just mentioned about. And as well, going further from where we are, now we've discussed about, okay, let's assume the function is differentiable, then it has a gradient. There is what we call the first optimality condition in optimization problem. And it says that the point at which the function is differentiable or the gradient of the function is equal to 0, that point is the minimum point of the function. That is, you always find your optimal point at the point whereby you have the gradient of the function being equal to 0. And that is what this first line is talking about, that if a point is the solution of the optimization problem, if the gradient of the function at point x is equal to 0. And as well as, yeah, the function is said to be convex if its adjacent or its second derivative is non-negative, is greater than or equal to 0. So these two key things can be used to verify what types of function you are dealing with, or to see where can you always find the solution of the function. And another consequence of the convexity is that we can define if a function is convex, then this inequality holds. And what this inequality is talking about is that when you have the gradient of the function can be approximated by what we call an affine function below it. So that's what the aspect of convexity in this case. And we also have, I think, not here, I have another way called the strongly convex. In this case, we have a parameter that will force this to always be greater than or equal to this variable. So I think we have that somewhere in the front. Now, coming to types of optimization problem, there are several types of optimization problem depending on the type of function we are dealing with. What is the type of the function f? In the simple case is when you have the function f to be a linear function, then you are dealing with a linear optimization problem. The other case is when you have a function f to be nonlinear, then in that case, you'll be dealing with nonlinear optimization problem. And as far as we have what we call the multi-objective optimization problem, in this case, you have several of f's. So you have f from f1 up to fk. So you have to minimize everything at the same time. In terms of application, this can can capture the idea you have to model, for example, air flights or the optimum performance of air flight in terms of considering several factors altogether. So basically, it can also be an mixed integer programming as well, or mixed integer optimization, depending on what is the behavior of your function f. Another types of optimization problem is the bi-level optimization, where you have two layers, the upper level and the lower level. At the upper level, you have an optimization problem whose, depending on the types of the bi-level, whether it is optimistic or pessimistic. So the second layer as well, which we call the lower level, is also an optimization problem whose solution set will determine the performance of the leader. The first, this F here, we call it the leader function, while this G is the follower function. So okay, before we go into, so these are just some examples of optimization problem that are obtained apart from this, but in terms of grouping, we can always group optimization problem into these three main categories. So the next is we are moving to, now let's go into non-linear optimization problem. Because aspects as well, I will work on the objective as bi-level optimization problem. So what for the case of this course, this discussion here today, I will majorly discuss about non-linear optimization problem. Another key thing is that though some concept of non-linear can be applied to the other two, but it's not always like that. Now coming to the non-linear optimization problem, a simple term, like in terms of modeling, if I have a point X here and I have to minimize point here. I don't know if you can see where this cursor is here. So I have a point. This is my minimum point. But I have this graph here. How do I get to this minimum point of this graph, starting from my initial point here? So to do this, though gradient descent says that you can always move gradually until you have the minimum point, until you reach the minimum point, which is the optimal solution of the problem. So what this is saying mathematically is that when you have your function giving an initial point x not in x, where x is a space, you have this be approximated using sk minus alpha k grad f of sk, where this alpha k is called the step size of the algorithm. So in other words, to explain this in these terms of graph here, you see that if I start from if I'm starting from here from the initial point, I can always move towards this solution based on the length of this step size. So a keynote from here is that this step size here can either be too big or too small. If the step size is too big, then the height rate will just keep moving here and there before it gets to the solution. It can take several iterations to get to the minimum solution. And as well, if it is too small, it's going to also move in a very little way to get to the optimal solution of the problem. So as we move along, we'll look at how does this really relate in terms of how can you improve the performance of the algorithm based on some key thing, either from the starting point or from the step size of the algorithm. In terms of 3D, this same curve here is the same thing I have here, but as we can see, the step size determines how the height rate move to the solution. So
hello, Doc.
yeah.
Thank you. Please, I want to give you a general information. In the next 2 minutes, our time will run out. So I will have to rejoin. So once the Zoom meeting goes off, you rejoin and then we are back to conclude. the
All right, thank you very
yes.
much, Prof.
Thank you. Thank you.
So going ahead, what I just discussed is this same iteration I have here can be we can formulate it here in terms of the way to put in the computer. It's just the same thing when you have the gradient descent moving gradually to the solution. So from the gradient descent, before I move further, let's just take note of some key thing. From here, I discussed about the step size, which is key. And as far as another property we can also look into is the function f itself. But for now, we can look at the step size. How does the step size affect the performance of the algorithm? And that's where it comes here, looking at the good and the bad step size. So the first result says that the gradient descent converges to a solution of the optimization problem if alpha k, which happens to be step size, satisfies alpha k being between 0 and 2 over L, where L is the Lipschitz constant of f. What does this mean? It means that if I try to choose the step size alpha k between this value is 0 and 2 over L, where L is just the rate at which the function is changing. So